Okay, folks, I'd like to spend a little bit of time with this ANOVA testing procedure. Hopefully get through this and then demonstrate this and find the solution with using either Excel, or I believe StatCrunch has a tool as well we can use on this. Just kind of reiterate where we left off on Friday. Remember, the null hypothesis is always going to be set up to where your 3 or 4 or 5, however many populations that you have, are assumed to be equal, okay? Because the test determines whether one or more are unequal, okay? So the assumption is that we start with equality, and then the data will then lead us either to reject that or to not reject it, okay? That means then, so if all my populations are equal, then my alternative has to be the complement of that idea, which would be that at least one of them is different or not equal to the others, okay? So those are, and like I said, that set of hypotheses is static. Okay, those are always going to be the same no matter what test or no matter what scenario or problem that we come across in ANOVA. Okay, now you might have more populations than just the 3 up there. You won't have 2. If you have 2, we could use then testing from the previous sections. Okay, so we've got this data here. Okay, when we put this into Excel on Friday, we came up with the sample means of each, okay? So the sample mean of 20.1 for New York. Texas had a sample mean of 18.2, and Oregon had 20.1. When I cut and paste these in the Word document, the X bar sub 1, I did not change that. That should say X bar sub 2, and that should say X bar sub 3. I didn't pay attention to that. So you might want to fix that if you printed the notes out. Step 2 is to find the variance of each sample. Okay, so we get those 3 values there. And then step 3 was to find what we call the grand mean, which is the mean of the means here. Okay, or you could take all 3 of these 10 data points, so add those 10 together, add those 10 together, add those 10 together, and then divide that sum by 30, and that provides you the grand mean. Okay, so the grand mean, another way to think about it, is the mean of every single data point that is provided. Okay, if you want to think about it as taking every sample and just putting it in one singular group and then finding the average of that one singular group, that is what we call the grand mean, and that's 19.47 in this situation. Okay. I think we talked on Friday a little bit that, you know, these are just samples. These are just 10 data values that came out of a population. So even though these are different, it does not mean that the populations are different. And if these were all 3 the same, it would not mean that the populations are the same. What we've got going on here is the idea that let's say that we go to an 11th data point in Texas. That 11th data point, which is a 11th value out of the population, might change this average to 20.1. Does that make sense? So we had that discussion where the samples, that's our starting point in the testing, but it does not lead us to say that this is true or not. Okay, we come up with the variances, come up with the grand mean, and then we come across this. And I think we had this written out for this class. I just want to reiterate what this is. This is the mean squares between. Okay, so what we're looking at there is we're going to be comparing how this variance relates to that variance relates to that variance. Okay, so we're looking at the between the individual groups. Okay, so comparing New York to Oregon to Texas. The way we do that is we take the sum of n sub I. So n sub I is the sample size. So n always refers to the sample size, and it's of the ith sample. That's how we read that. Okay. the sample size of the ith sample. So if n is 1, okay, if n is 1, we're looking at the sample size of the first sample, which was 10 objects. Okay, it might make sense. We don't have any limits on this summation here, okay, but it might make sense to say that n is going to start at 1 and it's going to go up to k, where k is the number of samples that you have. Okay, so n is going to start at 1, so n sub 1, and then it'll go to 2, and then it'll go to 3 because we have 3 samples here. Okay, so we should have 3 numbers that we're going to be adding together here in a moment. Okay, so we have the sample size of the ith sample. Okay, then we're going to multiply that by the sample mean of the ith sample. Okay, but I was 1, so we go to the sample 1, and it was 20.1. So we'll put 20.1 here, and then we'll subtract from that the grand mean, which was 19.47. Okay, we'll square that. That was when, so that was for sample 1. Okay, and that 10 was the sample size. I think generally people don't have any issues with these 2 values in here. It's this one out here that confuses people, because a lot of times, especially in this scenario, in this question, that number for sample 2 was the same as it was for sample 1, which will happen. Sometimes it'll be different, just because the concept, and I think maybe up here when we did this, you know, when we talked here, we said we could have n sub 1 be 100, we could have n sub 2 be 90, could n sub 3 be 85. They could be different numbers. The sample sizes can be differing, but they can also be the same size. And when they're the same size, I think that kind of confuses people. Why is it always this 10? Why did that get out there? Well, that's the sample 2 size. Okay. Then we're going to multiply that by x bar for sample 2. So x bar for sample 2 was 18.2. And then we'll subtract then the grand mean from that, 19.47. So this is what this refers to. So when I say, let's just kind of come down here in red and do this. When I say, you know, the summation is going to say you're going to take a bunch of these little things here and add them together, right? So when I is 1, so this would be n sub 1 times x bar sub 1 minus x double bar. That's when n equals 1. When n is 2, it'd be n sub 2 x bar sub 2 minus x double bar. And when n is 3, it'd be n sub 3 x bar sub 3 minus x double bar. And what these are the sample means. So the subscripts just tell you what sample they came from. So this subscript says that size, that sample size, came from sample 1, and this sample mean came from sample 1. Here it says the sample size of sample 2, and x bar sub 2 is the sample mean of sample 2. So that, I think that was it Texas? Yeah, it was the Texas sample. And then n being 3, so this would be the sample size of the third sample, and this would be then the sample mean of the third sample. Does that kind of make sense? So then we're going to add to that. Okay, so this would have been when I was 1. This would be when I is 2. And we have then when I is 3. So when we're looking at the third sample, its size was 10. Okay. Its sample mean was 20.1. And we subtract away the grand mean again, so 19.47. We found that out Friday on Excel. So we took the raw data that they gave us, and we just typed those into column A. So that was New York, this was Texas, this was Oregon. And then we just typed in equals average of that first column, equals average of that second column, equals average of that third column. Then we found the variance of each of those. Okay, so we'll need that in the next part. And the grand mean, we found two different ways. We said we could either average these three values to find the grand mean, or we could take these 30 values and average those, and that's how we get that number there, but they're the same. But sometimes, you're right, sometimes they'll give that to you. It just depends on the author and how the problem is presented. Sometimes they'll give you these values, sometimes they just give you the raw data and you have to come up with all of them. So K minus 1 is our denominator here. Okay, this is ultimately a degree of freedom concept. So K is the number of samples. So we had 3 samples, subtract 1 from that, we get 2. At the beginning up here when we started explaining this stuff, I think on Thursday, K minus 1, we labeled it as D dot F sub N. That N stands for numerator. Okay? And this D dot F sub D, that D stands for denominator. And what happens then, think about when we do this here, when we do that division to find our statistic, or F statistic, okay, MS sub B is this thing right here. So that K minus 1 is the degree of freedom for that numerator. Okay. MS sub W is that thing there. So N minus K is the degree of freedom for that denominator. Okay, so that's why those subscripts of N and D showed up previously. Okay, so we've got the variance between the groups. Now we want to find the variance within the groups. Okay, so now this will be looking at how these data points relate to one another, and how these relate to one another, and then how these relate to one another. Does that make sense? So now we're focusing on just one individual sample and looking at the data points compared to one another in that sample, instead of what we just did. What we just did was jumping from one sample to the next and comparing those. So in order to do that, we use this formula. Okay. Again, we'll go from I equaling 1 up to K. But we're going to take N sub I, which is the sample size, again, from the first sample, and subtract 1 from it. Okay, so our first sample size was 10. We'll subtract 1 from it. And then we're going to multiply that by the variance of sample 1. Well, the variance of sample 1 was 2.77. Okay, now make sure that you understand that this, so, because I is 1, so S sub I of 2, when I equals 1, would be S sub 1 squared like that. And that's the notation for variance, right? Okay, because we got a little bit further in 7th period last week, and they asked, well, why don't I square that number in my formula? Because variance is already squaring it. Does that make sense? Okay. S stands for standard deviation. S squared stands for variance, and we have variance out of Excel. Okay. So now, so that was when I equals 1. When I is 2, we're now looking at the sample size of sample 2, which again was 10. We'll remove 1 from it, and then the variance of sample 2, which was 5.733. So 5.733. And then we will add to that when I is 3, sample size of sample 3, minus 1, times the variance of sample 3, which I think was 4.1. Yeah. Times 4.1. And then we will divide that by N minus K. Okay? So N, I don't know that we've defined this yet throughout this, but N is the sum of the data points in all samples. So capital N is equal to N sub 1 plus N sub 2 plus N sub 3 all the way up to N sub K. So however many samples you have, you add up all of those sizes. So we had 3 samples. Each one had 10 in it. So in this case, N would be 30. Does that make sense? So it's adding up. It's basically counting how many values we had. Okay. So we have 30 minus K, where K was the number of samples. So 30 minus 3 will give me 27 there in my denominator. So now we have to type this stuff into our calculator. Okay, so typing in that first one, 10 times 20.1 minus 19.47 squared plus 10, 18.2 minus 19.47 squared plus 10, 20.1 minus 19.47 squared all over 2. So it gives me 12.0335. Okay. And then typing in mean squares within, so it'd be 10 minus 1. And we get that information. Okay. So this up here was mean squares between, this one was mean squares within, and we divide them in that order, between, over, within. Okay. So I'm going to take this number, so I'm just call this B for between, I'll call this W for within, and down here I'm going to take between divided by within, and I get 2.864. 2.864. Okay, so that number right there is referred to as our F statistic. That's our test. Okay, that's the number that we're going to compare to something else to decide whether we reject or fail to reject the null hypothesis. Okay. Now, we haven't talked about this, and this was step 0, which I told you on the way I've set this up, step 0 on Friday. We talked about how we'll do that later because I didn't think we had enough time to establish that concept on Friday and get as far as I wanted to. So, in a lot of problems, maybe you do this first. You find these critical values first before you run through and find the F statistic. The order really doesn't matter. But what we have to find out here, what we have to realize is that the F statistic, okay, and I'm just going to pull this up on GeoGebra so you can see the visual of what this distribution looks like. The F distribution, okay, is always going to start to the right of 0. It's always going to be positive, okay? And as we change the degrees of freedom, so let's just look at our particular situation here. We have a degree of freedom. So df sub 1 is, I believe the way this is set up, and I wish it had sub like n and sub d, but I believe the first degree of freedom is the k minus 1. So in that case, 2. And degrees of freedom for us would have, in the second one, would have been n, capital N minus k, so 27. So that is going to be our F distribution. And a lot of them look like this to where they are, you don't see that, before I've changed those degrees of freedom, you kind of saw that maximum, right? That kind of, that peak on the curve. Here we don't have that. But we always will have a skewed right distribution. It's always to the right of 0. So what we're going to do, the way that we decide to do a F distribution and an F test on this ANOVA structure is that you're always going to find a right area. Okay? So we're trying a right-tailed area. So we're trying to find an area like this. Okay? And that will be established by a critical value that I show you how to find here in a moment. Okay? And we can use GeoGebra, or I prefer Excel. But we'll find that F critical value. And then if our F statistic that we just found falls to the right, that means we'll reject the null hypothesis. Okay? So it's always going to be in an F distribution here. In this ANOVA testing, we're always going to be doing a right-tailed test. Okay? So one way of doing this is to click on this right-tailed object right here, that symbol is showing you that it's going to do the right tail. And if we want then to find our critical value, what we have to do is type in what we wanted our alpha to be. Okay? If we go back up to the original problem, it said we want a level of significance of alpha to be 10%. So if I'm going to use GeoGebra, I type in my degrees of freedom, and then down here, remember, this is your probability or your area that's getting kicked back to you. So I'll type in 0.1, and it's going to give me 2.5107. 2.5107. Okay? So that is my critical value. Does that make sense? Okay, that's the critical value that's attached to an area of 10%. All right? So that's how you'll do that in GeoGebra, if you like to use GeoGebra. If you're going to use Excel, you got to hit equals F dot INV. Okay, so it's going to ask me for a probability. So our probability is 0.1. All right, it says degrees of freedom 1, comma, degrees of freedom 2. Again, I'm going to go numerator, comma, denominator. So degrees of freedom in the numerator is 2. Degrees of freedom for the denominator was 27. And I think I've got the wrong. I think I actually have to hit F dot dist. Sorry. No, that's not right. Hold on. Just trying to give. Initially, I typed in f.inv, okay, which is going to give me the left tail, which we don't want the left tail, okay. So you'd have to do maybe some algebraic manipulation to get the right tail from that. It's just easier to go f.inv.rt for a right tail. You type in your probability, which is our alpha. You type in the degree of freedom, which is k minus 1 for your numerator. And you type in your degree of freedom, which is capital N minus k for your denominator. And that's the order. So alpha, k minus 1, and then capital N minus k. You hit that, and you get 2.5106. Is that the same 2.5106 that Excel was, or sorry, GeoGebra was trying? Okay, so what that tells us when we look at whether we are going to decide to reject or fail to reject, we're going to have this image for our distribution that looks like this. There's an area here. Okay, that area is alpha being 10%, and it is bounded by a critical value, sometimes called F sub C, of 2.5106. Okay, that would be that value right there. Okay, our test statistic falls to the right of that, correct? Our test statistic probably falls about maybe right there. Okay? So if it falls, so this red is the rejection region, just like always. So if our test statistic falls in that rejection region, we are going to come back up to our null hypothesis, and we are going to reject it. And if we reject the null hypothesis, that means that there is sufficient evidence to support the alternative hypothesis that at least one of the three populations is different. It doesn't tell which one, but one of them is different. Does that make sense? Okay. So what does that mean to us? Okay. Well, and so that's using critical values, which is fine. It works. Okay. But we also like to use, if we have critical value technique, we can use a p-value technique, can't we? So right now, what I'd like to look at is, so just to check this real quick, if I go f.dist, okay, and it says x, which is that one, comma, degree of freedom in the numerator, which was 2, degree of freedom in the denominator, which was 27, and then it says cumulative, so I'm going to say true, gives me 90%. So when I said cumulative, that's giving me my left areas. So if I subtract 1 from that, what do I get? Or that from 1, what do I get? 0.1. I get the 10%, which makes sense because 10% was our alpha, wasn't it? Okay. So what I'm trying to do here is show you that if I want to find the p-value of our f statistic, I can take f.dist, okay, type in my test statistic, which is 2.864, degree of freedom 2, degree of freedom 27, hit enter. Oh, I forgot to hit true, type in true. Type in true, hit enter, okay, gives me that. If I go 1 minus that, that shows me the area. So if we go back to our graphic that we had, I'm just going to draw on here. Okay, this was our area of alpha, right? Alpha was 10%. Okay, we put our test statistic in here, and our test statistic should be to the right, and it would be this red area, which this red area was 0.074, right? That's our p-value. Is the p-value less than alpha? It's 0.074 less than 10%. So just like always, do we reject h sub 0? Okay, so there I'm just trying to demonstrate that the main route we went was through using critical values. Okay, but that aligns still, as hypothesis testing has from day one, with the technique of using p-values as well. Yes? So it's f.dist, and then the f-test value, which was a 2.86 number, and then comma degree of freedom of the top, or the numerator, the degree of freedom of the denominator, and then comma true. And that's going to give you Q. So what that would do is it would add up everything. So we type that command in right here. So that was f.dist of my f statistic. I'll just call it x. Then degree of freedom of the numerator, and then degree of freedom of the denominator, and then we typed in true. That's going to actually give me the area here in yellow. So then we have to subtract that from 1 to get the area that is in red. Okay. So we fail, or sorry, in this case we reject the null hypothesis. One of these populations is different than the other. That make sense? Okay. Now that we've got Excel, hopefully we still got Excel open. What I want to do here is just demonstrate with you. Think about all the work that we just did. Okay, even going back to Friday when we came up with these means, grand mean, and variances. That worked. Okay, pretty substantial amount of work to test this, right? Okay, so you're going to go to data. All right, you're going to go to data analysis. Okay, now they don't have it. It's not labeled the same way as what we've been calling it. We call it ANOVA one-way testing. Okay, because we're dealing with one independent sample. Excel calls it ANOVA single factor or simple factors. Does it say simple or single? Single. Okay, ANOVA single factor. Okay, and it's the first thing that shows. It's the first tool in the data package. Hit OK. All right. Now it's going to ask you for the input range. Okay, so I'm going to click on that box. Okay, and go highlight my input range. So I'm going to highlight my raw data information. Okay. Just going to put it in there. It says group by columns or rows. So you've got to remember, how did I type these in? Okay, that first column was New York, second one was Texas, third one was Oregon, right? So I'm going by columns here. If you would have typed it in just like you saw it here in the notes, if you would have typed it in like this across, you just click the rows button. Okay. I don't have labels. I've got alpha to be 10% already. Okay. And then I'm going to put an output range. So I just want my output here to, I just click on a button or an empty cell that does not overlap my data to type my output. I don't know why I did that. Thank you. There we go. Output range, that's fine, and then hit OK. Well, what it's for whatever. Oh, my output range is the same right here. If you look at it, it says it's the same cell twice. So that's a problem. There, see how it says the same cell once? Okay, then hit OK. And it's going to give you this summary. And so the summary gives me all my averages, gives me all my variances, right? Okay, come down here. Gives me my numerator, MS is what they call it, okay? Gives me the denominator, which we came up to be 4.2-ish. Okay, if we go back to GeoGebra, we found it to be, because of rounding, we got 4.201. But you see those numbers reported, okay? Is that your F statistic that we found, 2.86? Now we found 2.864 because we had some rounding. They don't do any rounding here, okay? They give you, so what's nice about this is they give you the information that allows you to either compare using critical values. So I take F and compare it to F crit, okay, which is the critical value, right? And I can make my decision there. Or the most important value up there is the p-value. P-value is 7%. How does that compare to 10% alpha? It's less than. So we would reject. Okay. Do you see how that is much simpler than? Okay. Now, if we do StatCrunch, I don't know. Never done it. But I'm assuming that it's here and that it probably won't be that difficult. Yeah. So I'm just going to take my information from Excel, cut and paste. I would think that it will cut and paste into this. Yes, great. All right, so that's my information. I'm going to go to stats. Let's go to variance stats. One sample, nope. Two sample, nope. Where can we see this? See where it says ANOVA, where does it say ANOVA? There it is. There we go. All right, so we're ANOVA, we've got one way, right? Okay. Click that. Select the columns. Yep. This will allow you to get values in a single column. So if you had all 30 in the first column, I think this would allow you to kind of find breaking points for those. All right, so what you have to do here, if you click on this, is select more than one with Shift plus click. So I did that. Now I'm going to hit compute. And it gives you all that information. Okay. If you just start with like ANOVA, go one way, and just hit compute right away, see, so you must at least select one value or variable. So I have to there, and I want that one compared, and I want that one compared. Is that something we can do? So much easier using the tool, right? Okay. But if we just started using the tool and it spits back all these values of, the mean, the standard deviation, the standard error, SS, MS, F-stat, p-value, none of that makes sense to me because I don't know where it's coming from, right? But since we've gone through the formula now once, hopefully maybe we understand where those are coming from. The one thing that this does not do that Excel does do is this one forces me to have knowledge about how to use the p-value, okay? Because it does not report the critical value of a 2.86 number, which depending on, we should all be able to do either technique since we've been using both techniques for a long time. But you can see why textbooks introduce this p-value technique, because a lot of your statistical packages don't report or record the F critical value, or T critical value, or Z critical value for each of those tests. There is a 10.4 assignment. My hope is that you use StatCrunch or Excel and GeoGebra to complete that.